re-see this part. All right, so now what we're going to say is, let's say I have this particular reaction here with me. All right, it's just here. So let's say I have A plus B that is giving rise to C plus D, right? This is the reaction that I have with me. On my left hand side, what I have are called as my reactants. On my right hand side, what I have are called my products. If the concentration of my products is going to be higher, the reaction is going to be a forward reaction. Okay, so I'm just going to write this over here. Then what I'm going to have is going to be the forward reaction. And if the concentration of my products is going to be higher, then what I'm going to have with me is going to be my backward reaction. Okay, this brings us to understanding another concept of chemistry, which is that if you have the similar concentrations, okay, or let's say the amount of energy that we require to make A and B react with each other, okay, so that they could form C and D. If the same amount of energy is still present in your reaction, then the reaction will go to the completion, it will form the products, and instantaneously it will revert back from products to reactants, right? So this is something that you're going to see. So you're going to, your coffee's here. Okay, you're going to notice that you're going to have a reaction that goes further, and then you're going to have a reaction that comes backward as well. When such reactions take place simultaneously, okay, when you're going to have both the forward and the backward taking place, those kind of reactions are called as equilibrium reactions, okay, or those are the reactions that are going to never reach a point of completion as such. They're going to go forward, come back, go forward, come back, and this is going to keep on continuing. The reason for this is the concentration. What drives these reactions is the concentration. As and when you go on increasing the concentration of your products, the concentration of your reactants is going to go on decreasing. Okay, this is something which is very, very important that you remember, and you should be able to sort of write this down in proper wording. Okay, so this is basically what we say. Now if I wanted to look at this particular reaction, okay, and if I wanted to write down the rate of this particular equation, you would notice that your understanding of mathematics is very, very pivotal over here, because what we are going to use to write down this particular reaction over here is we are going to use the concept of differentiation. Okay, now before this also I have written down on multiple occasions that, okay, dt or dA by dt or d by dt, that is how your differentiation works, right? So we have used this particular concept in many other places as well, but here specifically we are going to use the process of differentiation, and we are going to define that process as well. So let's say I have this particular reaction with me where I have A, B making your C and D, but we don't know what stoichiometric coefficients they have. So we're going to add the stoichiometric coefficients. So I'm going to say A, B is giving rise to C and D, right? So these are my stoichiometric coefficients. Now, if I wanted to find out what is going to be the rate of my reaction, okay, I could say that, let's say my rate of reaction, okay, is going to be the concentration of A multiplied by the coefficient, the concentration of B multiplied by the coefficient. Okay, this is something I have with me. This can also then be written in the form of differentiation, where I could say that the total concentration of my reactants over a period of time when they get converted into my products is going to be equal to, I'm going to add my rate constant here. Okay, why am I adding rate constant? Because I cannot have a reaction which does not have a standard value with it. Okay, so the K over here is going to be my rate constant. I'm going to write this down here in case you forget. The rate constant. Okay, so rate constant into concentration of A. Okay, whatever the concentration of A is going to be, raised to its coefficient value, and the concentration of B raised to its coefficient value. This particular reaction that you have with you, okay, this particular, not reaction, but this particular formula that you have with you, okay, this equation or this formula is called as the differential rate equation. So I'm just going to put it down over here. Differential rate equation. Right now, this is a very important concept, because using this particular rate reaction or rate equation, what you can do is you can find out certain things about your chemical reaction. Okay, this particular thing can also be referred to as the rate law. Okay, so I'm just going to write this over here, something which is called as your rate law. Okay, now just like you would use a particular value as a standard whenever you are converting your currencies from one form of currency into another form of currency, or currency of one country to the currency of other country, you use something which is called as rate conversion factor, right? Similar to that, in your chemical reactions also, there is a particular law that you use whenever you say that your reaction is going from the beginning to the completion factor. And when this happens, okay, you want to use something which is called as rate law. Now, what is a rate law? Rate law is nothing but a chemical equation, okay, where you have your concentrations or molar concentrations of your reactants given to you, okay, and in each of these, okay, the stoichiometric coefficients, which we just wrote here, if you write A and B and B, let's say, okay, I'm just giving you an example. So you are going to say that you are going to have these molar concentrations of your substances, okay, or reactants basically. So these are your reactants. So the molar concentrations of reactants with what? With their more stoichiometric coefficients that are going to play an important part in order to make a balanced chemical equation. If you wanted to write down the balanced equation for this particular reaction, okay, if you wanted to write down the rate reaction for this particular equation, what you would need in order to complete that particular part is the molar concentrations as well as the stoichiometric coefficients of each one of your reactants. Okay, if you are able to get this, you would be able to write down your reactions in proper manner, and you would also be able to make sure that your reaction is balanced. Okay, if you are understanding anything of what I'm speaking, can I please see a thumbs up so that I understand that I spoke something and you understood it? Yes, can I have a feedback, please? If you did not understand, what I could do is I could just go over the part one more time. Yes, can I please see a virtual thumbs up? And also let me know if you are able to see my screen properly, or do I need to move my screen a little bit here and there so that all the parts of my screen are visible? Is everything on my screen visible, or is there something blocking my screen? Because I do have multiple windows open here. Children, a feedback is very important. And listen, until you speak, I'm not gonna know if you are understanding. Kushi, can you please let me know if whatever I'm speaking is making sense? Is it?
Ma'am, could you please repeat, just like a really quick repeat?
Version? Yes, we can do. Okay, so we are understanding in this particular concept that your rate of reaction is dependent on three major things. Okay, the first one happens to be the concentration of your reactants, then temperature and catalyst. At this point, we understand that if you are going to have a particular concentration of your reactants, for example, I have a cup of coffee here. Okay, in order for me to make I don't have coffee anymore. So if you needed to make a cup of coffee, what I would need is I would need a certain concentration of coffee, sugar, some amount of cinnamon, cream, and milk. Right? If I have these things together with me, I could possibly make a cup of coffee, right? But in order for me to make this cup of coffee, certain things are required in a particular concentration. If I need to make this big cup of coffee, I possibly cannot take 1 ml of milk and add to it 1 mg, or let's say 1 gram of coffee. What I would make would not be a liquid cappuccino. What I would be making would be a concentrated decoction of my coffee, which is something I'm not looking forward to. Okay. So this takes me to a point of understanding that if I have certain reactants, their quantities, okay, quantities which in chemistry you represent by the term stoichiometric coefficient. Stoichiometric coefficient is the amount of a substance that you have of a particular reactant. Okay, so if I say I have 1 tablespoon of coffee, and if I have 1 teaspoon of sugar, and I have a pinch of cinnamon, and I have a dash of cream and half a cup of milk, those concentrations are really, really important for me to make a good cup of coffee. This is essentially what you have to understand in this particular equation. But if I wanted to be a very, very scientific person, like let's say I want to run a cafe, and every single time I want to make coffee, my coffee has to be perfect. It has to have that perfect flavor every single time I make it. If that is my condition, I need to have the exact concentrations written down somewhere, and I should have a formula to do that. So that whenever I carry out this particular reaction, it always gives me the same outcome. In order to do that, what we use is something called as the rate law. What does the rate law say? Rate law says that in order to write down a perfectly balanced equation, I need to know two things. I need to know the molar concentration of my reactants, and along with the molar concentration of the reactants, I need to know that this molar concentration of the reactants is written as the stoichiometric coefficients of those molar concentrations, which means 2 moles of milk, okay, and 1.3 moles of cream, 0.7 moles of coffee, and 0.2 moles of cinnamon. This is the concentration of the reactants to make the perfect cup of coffee. If you ever have chance to make coffee, just try this. Okay, it makes like mind-blowing coffee. You cannot beat this coffee ever. Okay. So this is something that you could do if you knew the concentration of your reactants. No matter where you would make this coffee, it would always and always and always turn out to taste the same, unless you change the kind of milk. Instead of using buffalo milk, if you start using human milk or cow milk or goat milk or yak milk, then the tastes might differ. Okay, because what you're doing is you're not changing the molar concentration of the substance, you're changing the substance itself. Okay, that also gets us to understand that a particular reaction, if it uses the same components but different substances. Okay, now understand, when I say same components but different substances, I mean you could use a salt and you could use a sugar, okay, and some water to make a solution. When I say a salt, it could be magnesium salt, it could be ammonium salt, or it could be your table salt. That is not defined in this particular reaction here. It just says take certain amount of sugar. Let's say it says 2 moles of salt and 3 moles of sugar and 11 moles of water. That is understood. Okay, sugar means some sugar, salt means some salt, and water means any sort of water. It could be boiling water, it could be water in the form of steam, it could be distilled water. It's a very general reaction that is given to you. You can make this reaction very, very specific by writing ammonium salt. Sugar could be your dextrose sugar, and water could be distilled water. And now what you have is a specific rate for which this reaction will go ahead. You know these concentrations, and using these concentrations, you would be able to find out their rate. If I'm going to give you an actual example instead of just your example for coffee, okay, I could write this particular equation, look at it very, very carefully, and try to understand what is happening. I have 2NO in the gaseous form, okay, and I have my oxygen in the gaseous form here. When these two are reacted with each other, what I get is 2NO2 in the gaseous form. Okay. If I wanted to write the rate of this particular reaction, I would say rate is equal to rate constant, okay, multiplied by the concentrations of the reactants raised to their stoichiometric value. Say that sentence over and over again till it makes sense. Rate is equal to the rate constant into the concentration of the reactants raised to its stoichiometric value. Rate constant multiplied by the concentration of the reactants raised to its stoichiometric value. How would I write this down? My first reactant is NO. So I'm going to write NO. What is its stoichiometric coefficient? It is 2. So NO in bracket, the molar concentration of NO raised to the stoichiometric coefficient, which is 2. What is my second reactant? It is O2, and it is raised to 1, which technically, even if you don't write, makes no difference. This is what my rate constant is going to be. Should I write this down, what I would get will be my value or the rate of this particular reaction. Okay, now there is something which comes into picture when we write this down, something which is called as the order of reaction. Okay, so I'm going to write this over here. Order of reaction. Okay, now it is not what it sounds like. Order of reaction does not mean whether my reaction 1 took place first or my reaction 2 took place first. No, the order of reaction, okay, is basically the sum of the powers of the concentrations of the reactants. What are the powers of my reaction? Can anyone tell me if I wrote something like AA plus BB is going to give me CC plus CD? If this is my reaction, and I say that the rate of this reaction is equal to reaction constant or rate constant into the molar concentration of A raised to its stoichiometric value, reaction rate of B raised to my B. Okay, the concentration of B raised to B. This is something I have. This is my rate. Now, what would you say if I asked you to tell me the sum of the powers of the concentration? What am I talking about? Am I talking about the capital A's, or am I talking about the lowercase a and b?
Lowercase.
Exactly. So here in this particular form, okay, what my exponents or what my powers happen to be are A and B. Okay, so this is like A and B. Okay, now what I'm going to do is I'm going to take some of the powers of the concentration of the reactants in the rate law expression, and this is going to basically give me the order of my reaction. The order of reaction can be 0, 1, 2, 3. It can be fractions. It can be something like 1.13 3. It can be 1 divided by 47. Whatever the sum comes, the sum is. Okay. This is a very, very important point for us to remember. So we're gonna note this down in our notebooks so that we are 100% sure that this is something that we have understood. So I'm gonna write this down, and I would appreciate if you noted it down with me. The sum of powers of the concentration, powers of the concentration of the reactants. Make this a little small so you can write it together. Rate of reactants in the rate law expression. This is called as the rate law expression. Okay, so rate law expression is called as the order of the reaction. It could be 0, 1, 2, 3, or even a fraction. Easy peasy. Okay, now if we are going to write all of this, okay, if we are going to go over and if we are going to find out the rate of reactions, and if we are going to say, okay, I don't only want to find out the rate of reaction, what I also want to do is I also want to find out how this rate of reaction is going to be written down, and so many other things are something that you're interested in finding out. I know logically you guys are not interested in this particular thing, but for the process of examination, let's assume you are. What you would need to know in this particular format, okay, if you were to solve all of these, is something which is going to tell you how much or what is the quantity of this particular thing that you're doing, which means that you would need to deal with something called as your units. Right now, whenever you write the units, okay, you are going to use moles and the duration. If you go over, okay, the first concept that we spoke, 2 moles of a substance get converted into a product in several seconds. Okay, whatever number of seconds, which means that your units for writing these reactions would be moles per minute, moles per second, or however it goes. Okay, so how many number of moles divided by the time that you used. These are going to be different. Okay, just give me a second. Just getting a call. So these are going to be constant for a particular kind of order of reaction that you have. We're just going to make a table here. Okay, again, you can find this table in any of the literature that you would read for studying, but if you note it down along with the class, it really helps you in actually understanding why a particular quantity is being placed in your table. So I would suggest that while I write it down on your screen, you should also note it down. It would just really help you understanding what is happening over here. Okay, so we're going to put this down. The coffee is all cold. So here, in here, okay. Now, very, very important that you understand that rate is written with. I know I have said this multiple times, but I will say it few more times till it becomes a sentence that you can speak any single time of your day whenever asked. Rate is going to be found out by writing the rate constant multiplied by the molar concentration of a substance raised to the stoichiometric coefficient. This is my rate of a particular reaction. I could also write the value of K. Okay, now this is the equation that I have. If I reshuffle this, I can write it as K is equal to rate divided by molar concentration of A multiplied or raised to the stoichiometric coefficient, molar concentration of B raised to its stoichiometric coefficient. This could also be rewritten as concentration divided by time. Concentration divided by time, okay, multiplied by 1 divided by whatever concentration you have. Whatever concentration you have with you will give you this particular equation. Okay, so in your numericals, you may not be able to use your rate constant or the rate law as it is given to you. You may not be able to use your what is called as your rate law expression as it is given to you. Okay, but what you would be able to do is rearrange your formulae, and by rearranging the formulae you would get these different values, which then could be provided to you by your teacher when you're solving the numerical, and it would just make sense. Okay, agar mujhe ye diya hua hai, this is what I should have. Now, there are different orders of reactions that we are going to talk about. So I'm going to say order of reaction here. Okay, this is going to be my order of reaction. Then what I'm going to have is the order, or I could just say the type of reaction. And then here I will have units. Okay, now let's say the first thing I talk about is my zero order reaction. Okay, what is the order? Zero. How would I write this? Molar concentration, okay, divided by the time multiplied by 1 into moles per liter. Okay, this is going to be moles per liter. This is also going to be moles per liter, but you are going to write down the order on the superscript over here. So this value is really, really important for you to remember. Okay, what is this value? Zero. This zero is technically nothing but the order of your reaction. Okay, so I have highlighted it. I've added some sparkle to it so that you would be able to remember. If you are not able to remember it, please find a different way to make this seem important to you and put it down in your notebook. Now, if I learn a lesson from this, okay, if I say that, okay, this is going to tell me what kind of reaction the first order reaction would be, if I am understanding something, okay, I would say I have first order reaction, which means that the order of my reaction is 1. So moles per liter. Okay, so this would be per liter would be written as my -1. Okay, or I could just simply write L. So moles per liter upon the time that it took multiplied by 1 upon moles per liter into 1. Right, this is something that I would get as my first order reaction. If I was to solve these and find out an easier way to write this, this would become moles per liter per second. Okay, you could also write this as moles liter in this way. Both are pronounced in the same way, moles per liters per second. Here, what you would get would be, again, moles per liters per second. Okay, so the values are going to remain the same. The units are going to remain the same. It's just that the numbers that you add over here are going to differ. Based on this particular point that we discussed, what I would want you to do in your notebook is complete this part. Okay, so you're going to write it down for your third order reaction, and then you're going to let me know if you were able to do that. So write by yourself. Okay, Is everyone understanding till this part? Whatever I spoke, did that make sense? Or should we go over this part one more time? If no one says anything, I'm just gonna go on to the next part. Yes, have you understood what I spoke? Okay, assuming that you understood, okay, we are gonna go ahead. Now let's say I am a kind of person, okay, who just can't seem to leave this point as it is. Okay, if I have to go over, and if I have to say that I need to also plot a graph about the same, okay, because just writing a particular chemical equation is not cutting it for me. So what I could do is I could make a graph in this particular manner. Okay, now look at the graph. Try to understand what is happening in this particular diagram here, or in this graph here. So my one axis would be here. This would be my other axis. Okay, I'm going to draw one line here. You would understand why in a minute. One here and one here. Now let's remove our scale. Okay, here I'm counting my time. Okay, and on other axis I'm plotting my rate, which obviously is going to be written as dA or dA by dt. Okay, rate is also represented by k here. Okay, this is going to be my k value. Okay, so let's understand what this is doing now. So if I say, okay, at a particular point of time or at a particular rate, okay, I get a particular kind of graph. Okay, right now I'm just gonna say at a particular kind of point in my reaction, okay, I am going to see that my rate. Yes, did someone just unmute themselves or say something right now?
Yes, ma'am.
This part, tell me.
Ma'am, means we want some notes so that we can refer it afterwards. So how can we write some notes? Can
You
you just?
could basically copy all the things that are there on the screen. Okay, or what you could do is you could use my notes. So I have created some of the notes which I have on my screen right now. What I would do is I would share them with you. Would that work? But then my notes don't have anything except the thing that I put on and just some sort of explanations. So I think if you could just go through the class again and note whatever I'm speaking, and just like kind of put it down in the words, that would be more than enough amount of notes for you as such. And you should not have to make anything more. Just kind of print out everything that I have on my screen and just add your annotations to it, and that should be more than okay. Because when I have made these notes, I have referred to several books, and then I have compiled all of the data together. So if you refer 4 or 5 books, you would be able to find the same data in them. Just
So, ma'am, you have the notes written with you, right?
yeah, I sort of do have them, but again, like I said, it's just the same thing, but instead of just writing time, I have written like what I'm supposed to speak here. If you want, I could share those with you. I don't know how useful they're going to be for you, because it's basically just all that I'm speaking. And you
No,
could
ma'am. Please share it.
I will. I will. I would also suggest you to look at this particular website. Okay, it is called as Lumen Learning. It is not specifically meant for CBSE. I'll write the name over here. Okay, Lumen Learning. This is a website that has been created specifically for the Cambridge Board IGCSE, but they have very good explanation of the topics. Okay, so you want to do a thing which is you want to write chemical kinetics, then lumen learning. And what you would get is a more sophisticated way of noting down the things. Okay, so most of my notes are following the pattern from Lumen Learning. So you could just refer to Lumen Learning and see if you understand that. If it doesn't help, I'll share more resources with you. Okay, would that
Yes,
work?
ma'am.
Will you give it a try?
Yes, ma'am.
Yes.
Yes, ma'am.
This is a very good site for you to actually learn all by yourself, in case you're not able to understand what the teacher is saying, but you want to hear how a person would explain it to you. The Lumen Learning is written in a way that a person would be talking to you, so it seems like the website is actually communicating, and it has like examples at the end, and it also has this interactive way where you can go back and forth, and there are some numericals in the end of the particular concept. So it feels like a very interactive website. So you just give it a try. Okay. So just coming back to this point. Okay. Now this is a particular graph that I have. Again, I am not going into the specifics of what this graph is right now. We will discuss and then we will put the labels onto this. Okay. Now let's say if I have my zero order reaction. Okay. Wherein what I am saying is that the rate of my reaction, okay, is proportional to zero power. So at the top of these reactions that I have, the coefficients that I'm going to use are zero, which means that whenever my reactants, okay, so we are going to write reactants are going to get converted to products, okay. What is the thing that I am saying? I'm saying that the rate of reaction, okay, is going to be zero, right? This is the value, or this is the cue that I have, that okay, this reaction is going to be my zero order reaction. This particular graph represents that reaction, okay, where you understand that the rate of this reaction is nothing but K into the concentration of the products raised to zero, okay, which could also be written as K into 1. Okay, so I'm going to write this as K into 1, because the concentration of reactants raised to 0 is nothing but the concentration of the reactants, which is going to be 1. If you have pure substances, their coefficient, if it is not mentioned, is always going to be 1. Okay, so if I say I have sodium, but I don't tell you how much sodium, you are to go ahead and assume I have 1 concentration of sodium, which is 1 mole. Okay, if it is not mentioned, it is always 1. Now if I take these two reactions, okay, if I note this down here with me, I'm going to write two parts. I hope you are able to follow after I write them down. The first part that I'm going to say is I have D of my reactants divided by dt. Okay, so dr by dt is going to give me the rate reaction for my reactants raised to 0. I can also rewrite the same thing as rate is equal to dr by dt, okay, of what, where my K is multiplied by 1, because the concentration of my reactants is 1. If I take both these sides, okay, if I basically take my left hand side and my right hand side together, and if I was to note them down in a particular manner, I could also rewrite this particular part as the amount of my reactants is basically giving me K dt. So this comes here, this gets multiplied here. 1 into dr is going to remain dr. Okay, now if I have this particular reaction with me, if you were to integrate, again, concepts of your mathematics are really important. Unfortunately, I cannot teach you what is integrating and what is differentiation, because I don't know it myself. Okay, all I learned is, agar uske samne likha hai integrate karna, I need to add I as the constant of integration, and what I need to do is I need to remove the d and d from both the sides. So upar agar d hai, niche agar d hai, differentiation ka d goes away when I write integration. This is what I know, because I never took math after my 9th standard. Okay, so I will not be able to help you with how you integrate and how you differentiate. Also, it is not required in chemistry for you to note down the entire derivation of your equations. All you need to do is you just need to say that you're going to integrate both the sides. When you integrate both the sides, what you get is your R is equal to negative KT plus 1. Okay, 1, or you could also write it as I. I is going to be your constant of integration. Is that making sense? Differentiation में d लिखते हैं, integration में d को उड़ा देते हैं. Even if you understand this, you would have understood two very important concepts of math. That is all. Okay, this is how our chemistry teachers have gone over and taught this to us. Now, if I say, okay, at a particular period of time, my concentration of a reactant is certain number, which means that if I talk about time 0, okay, at time 0, if I say this is 1 minute and this is 2 minutes and this is 3 minutes, the concentration of my reactant is going to be at its highest point, right? And then as the time is going to pass, the concentration of my reactants is going to go on declining. Does that make sense? Does this particular sentence follow through with what I spoke? At 0, the concentration of reactants is higher. As the time passes, the concentration of the reactants will go on decreasing, which means that I could look at this graph in another way and I could draw it in this particular manner. Okay, so we're going to take this over here. We're going to make another graph. At this point, I'm pretty sure chemistry feels more like math to you, and it is going to do that for certain classes. Okay, until you understand what exactly you are supposed to take as constant and what exact values do you need to take as your independent values. Once you do that, graphing and calculations is going to feel like a piece of cake. Okay, so here I'm going to put time, and on this side I'm going to put concentration. What I said is at time 0, the concentration of my products. Okay, so I'm going to put this as my time 0. At time 0, the concentration of my products is really, really high. The rate of my reaction, or the rate constant, is going to give me a negative slope if I plot this. This formula tells me this concept. This formula tells me this concept. Would that be something you were able to follow, or do I need to make it in more easier sentence? Is this something that you were able to understand? Yes, kids?
Ma'am, can you repeat the last part?
So the last part here, okay. Again, giving you example of my coffee. At the time 0, as soon as my coffee is served to me, the concentration of coffee is higher and the time that I am holding my cup is the lowest possible. I just got the cup of coffee. Time 0, concentration at high. As in when I would sip it, the concentration would go on lowering. If I was to put a diagram of how much amount of quantity of coffee is present in my cup, if I was to say this is my cup and this is the concentration in the beginning, at different times, the concentration of the coffee is going to go on decreasing. And if I graphed it, this is something I would see at, okay, this particular line shows the slope of the reaction or the slope of the graph. And because it is declining from higher to lower, I would say I get a negative slope. If you saw, okay, this particular thing when the coffee was made and it was being poured into my cup, the concentration at time 0 would be low. Time 1, concentration would increase. Time 2, concentration would increase. 3, 4, and 5. So here this would be my time 0. This would be my time at whatever initial. This would be my time 0 here, and this would be Tn. For this particular example, if I made a graph, my slope would indicate a positive value. The reason my slope would indicate a positive value is because I started at a concentration that was lower and I ended at a concentration that was higher. This is the mathematical concept that unfortunately you're going to be learning for about 3 chapters in your math, and it would probably not make sense even after that, but in chemistry it's just that logical. Concentration नीचे होते जाएगा, slope will be negative. Concentration ऊपर होते जाएगा, slope will be positive. If you understand this, graphing, the chapter graphing is going to be a piece of cake for you. ठीक है? इतना समझ में आ रहा है? Based on this, you would be able to visualize any kind of graph and what you would be able to do. Now, let's say I don't know all the values. Okay, I was just drinking my cup of coffee. I never really made a graph by every sip that I took. But if I wanted to find out that at this particular time, how much coffee did I have? Using this graph, I could plot it this way. Okay, trust me, no one is interested in knowing this except your examiner, who also are not interested in knowing this. They're interested in knowing if you have understood this concept. So you would graph it, you would plot your graph in this way, you would draw a dotted line, and you would say at this particular time, let's call it as my time 1, because my graph already has a linear progression and it shows me a negative slope. If I was to take a particular point and join the two values at time 1, my concentration would be this. In using this, I could find out any particular concentration at any particular point of time. All that I would need to have are two quantities, the one at the start, one at the end. If I have few in the middle, nothing as good as that. If I don't have, totally cool. I just need to know at what concentration I started, what concentration I ended, what was the time at the beginning of the reaction, what was the time at the end of the reaction. If I have these values, I'm all set. Let's look at a real-time example to understand this better, because although your cameras are off, I could make out that you guys are just like, I don't even know what this lady is talking about. So I'm going to give you an example, because I don't like it when children say, I don't know what this lady is talking about.
Ma'am,
Yes, sir.
ma'am, is the graph always linear?
The graph would be linear in ideal conditions. If your graph is not linear, okay, what you would do is you would plot a graph that does not cross through 0, does not pass through 0, but gets at least 2 points on the line. Okay, and if your graph is not getting a linear line, you probably noted your values wrong, because it has to have a progression that is either going up or going down. If your values give you a straight graph, a straight line, your values are almost perfect. I'll tell you a cheat code in examinations. Okay, if you have to note this down in the practical component, let's say your teacher has given you a practical to do and you don't really want to solve all of that, like you might have done it for your titration. No one really wants to do titration. That's the point of all of this. So you run the pilot titration and then you just randomly write values, like agar your pilot value was 9.8, उसको आगे पीछे करके 9.7, 9.8, 9.6 you take and you do the averaging. Just like that, even in these particular kind of rates of reactions, wherever you have to calculate, find out at what time it started and find out at what time it ended. And uske beech wale plots point plot kar do and your reaction would be fine. Just don't plot exact values, because no one, okay, literally no one, not even your teacher, is going to get those exact points. So an error of plus and minus 2 or 3 points is totally acceptable, which is called as the human error, which is considered during the process of calculation. And this is also why the rate of reaction calculated and the rate of reaction estimated are different values. There is going to be an askew that was going to be seen, or there's going to be a error point that is going to be seen whenever you estimate the rate of reaction and then you actually theoretically practically calculate the rate of reaction. So theoretically a rate of reaction could be A, and practically it could be B, and those values could go up and down depending on how good you are at your practicals. Never be too good at practicals, because that would raise a lot of questions कि like तुमने इतना अच्छे से practical कर कैसे लिया. थोड़ा सा पॉइंट्स प्लॉट करते वक्त थोड़ा सा दिमाग यूज करके एकदम सही सही पॉइंट्स नहीं प्लॉट करो. स्टार्टिंग वाला प्लॉट करो, एंड वाला प्लॉट करो, बाकी सारे वैल्यूज पेंसिल से लिख के रखो. once you see that at least you have 2 points passing through the line, तीसरे वाले को थोड़ा ऊपर या नीचे करके उस लाइन के आसपास लेके आओ. which means that if you found out certain points and if your points looked something like this, okay, what you can do is, इन दोनों के बारे में तो तुम कुछ नहीं कर सकते, these have come really wrong, but you can definitely make this value come here by altering certain calculations in your paper. Okay, if you do not do this, your line will never pass through 2 points and you will not get marks. Does that make sense? Would you use this knowledge for the benefit and not for copying? Now you know that you don't have to copy for this particular chapter because there's a logic on how to solve these things. Okay, so please refrain from copying in the examination. Now let me give you an example. I have ammonia with me, okay, and because like chemistry people are like really rich, I am going to take this ammonia and I'm going to place it on platinum, because why not? Okay, like if you have the equipment, use it. So I'm going to take NH3, note the stoichiometric coefficient. This is in gaseous state. I am going to take this, I am going to heat this at 1130 Kelvin. Now, just to make your life a little confusing, they will not give you the temperature in degrees, they will give you the temperature in kelvins. You might have to convert them into kelvins to degrees. Now, lucky for me, I have someone who would do this for me, which is people like you, students, who would just tell me, okay, if you convert, this would be the answer. Unfortunately for you, you have to calculate it. So I request you to learn the calculation of Kelvin to degrees to Fahrenheit as soon as possible. Okay, learn how to convert these things. Also learn how to convert 1 gram to 1 milligram to 1 kilogram to 1 liter. There is a very easy formula. Okay, if you take 1 milligram of a substance, okay, I'm just telling you a relation over here, or let's say I take 1 microgram. Okay, microgram is really small quantity. If I take 1 microgram of a substance and I put it in 1 liter of solution, what I get is 1 molar solution of that particular substance. Now, using this particular formula, what you can do is, if you wanted to make 2 molar substance, you could change this value or you could change this value. Let's say you already weighed out 1 microgram because it's really small quantity and you're like, bus, ab aur nahi. So what you can do is you can change this concentration to 0.5 liters. And there you go, you made 2 molar solution. These way, there are many other conversions that you can use to make your calculations easy as a piece of cake. If you learn it, it'll be really good for you. If you don't learn it, it's going to be difficult to solve this in the period of time that you would be given to write your exam. Okay, so just learn the tricks of the trade so that you score better in chemistry. Now what I'm going to do is I'm going to take platinum. Okay, I'm going to put this on platinum surface because platinum gives you the higher melting point. Platinum does not melt at a very high temperature. So you can use the platinum surface so that you can raise the temperature of your ammonia to higher point. Okay, which means that at this point, your platinum is working as a catalyst. Is your platinum taking part in the reaction? No. Is your platinum getting decomposed in the reaction? No. Are you able to use the platinum for the next reaction? Yes. By that logic, platinum is your catalyst. Okay. Now, if I do this reaction, what I get is N2 in the gaseous form in 3 moles of hydrogen. This is by decomposition reaction. If I was to write the rate, I would write it for the zero order reaction NH3 0K. Okay, this is the rate of my reaction. I could do the same thing for the decomposition of my iodine multiplied by my hydrogen, okay, Hi. But what I would use there would be gold. Okay, so this is something that you are going to use in order to understand these reactions. If my reaction is first order reaction, this was when it was a zero order reaction. If I have first order reaction, then my graph is going to look a little different. I will show it to you how my graph is going to look. So here I have this one and this one, and I want to plot one line here and I want to plot one line here. Okay, this is going to be for my time. This is going to be for my rate. So we're going to put it this way. Okay, now understand what I am doing in this particular graph. Look at the first graph, a linear line for D0. That is my first order reaction or zero order reaction. When I have my first order reaction, okay, what I'm gonna have is the rate of my A at the beginning of the reaction, and as the reaction proceeds, okay, what I'm gonna see is there is going to be exponential decay. I'm gonna put this down first, okay, and I'm gonna say I have exponential decay. If you're good at words, you would know that exponential decay is something that you have also learned, not in the same terminology, but is something that you learned when you are learning the chapter of radioactivity in grade 10. Okay, or even in your 11th standard, you had radioactivity. I guess that was your 13th or 14th chapter, okay, radioactivity. So what you learned there is, if I have one unit of a substance, after it has given out alpha and beta rays, okay, once it has given out alpha rays, it will give out beta rays. Once alpha and beta rays have been given out, it will also give out gamma rays. When it is doing that, alpha will decrease the mass of my substance by a certain quantity. Beta will decrease the mass of the substance by a certain quantity. Gamma will also decrease the mass by some quantity, not very significant, but it will decrease the quantity of the mass I have. When this happens, I would say my substance reaches half of its entire original mass. Okay, then what I would see is what I calculated the period for this particular reaction to happen from 1 to 0.5 is my half-life. One calculation. Next time when I want to calculate the half-life, what I'm going to see is I'm going to make half of the half. So this is going to become 0.25. This is then going to be broken down into more half. Okay, so this is going to become 0.125. And this is going to go on decreasing exponentially like this. This is called as my exponential decay. where you are not going to make half and half and half of the product that you have with you. Instead, you are going to consider whatever value you have as the initial value again, and you're going to break that into half. And then you're going to break that value again into half and into half. This way, the decay never really stops. Okay, this kind of decay is going to go on continuing, and therefore this is called as your exponential decay. Okay, so in my first order reaction, what I am going to see is that my graph is going to show me exponential decay and is not a linear graph. So Parth, to answer your question, the graph is going to be linear if it is your zero order reaction. If it is your first order reaction, the graph is non-linear but follows an exponential decay format. Okay, now if your reaction does not follow this, use the same trick and see that you get your next value a little ahead so that your graph is not a straight line. It has a curvature. Okay, this makes sense. Were you able to follow this part of the particular concept that I spoke right now? Did it make sense or did it make sense? Yes, children, was I saying something that you understood? Okay, Parth says yes. All right, so this is something that I'm going to leave you here with. Okay, for right now, understand that sometimes your reactions could represent the first order reaction, but they may not be first order reactions. I know it is really confusing. Do they look like first order reactions? Do they not behave like first order reactions? We need to find out. But whenever these reactions are not first order, but under certain conditions seem to behave like first order reactions, we're going to call them as pseudo. Okay, pseudo means false. If you took biology till 10th standard, you know pseudopodia means false feet. Pseudo first order reaction, false first order reaction. These are the first, or these are not the first order reactions, but under certain conditions, maybe a lot of pressure or maybe a lot of increase in the temperature or maybe a little amount of catalyst, more amount of catalyst, under certain conditions like that, these reactions seem to behave like first order reactions. But if they don't behave like that, they could be second order, third order, or any other kind of reaction. But they seem to represent that kind of reaction. So we call them as your pseudo first order reaction. Okay. Next time when we meet, what we are going to do is we are going to find out what is the way in which you can find out the K, that is the slope of your reaction. Okay. The next thing that we are going to do is we are going to find out how exactly to write the half-life. Okay, I kind of explained you the half-life here, but we are going to just note down how you can find out the half-life of a particular reaction. Once you find out the half-life of the particular reaction, the next thing that we are going to do, just give me a second, let me just look at your textbook. Okay, the next thing that we need to do is to learn how exactly your time and the pressure. Okay, so time and pressure graph is something that we are going to learn about. Then we are going to learn about the mechanism of your reactions. And the next thing that we are going to do is we are going to discuss how the temperature is going to play a part in your calculations of your rates of reactions. Okay, so one more, not one more, actually two more classes, and we are done with your chemical kinetics as well. I would request you to note down all of these parts of the class in your notebook. I would share the recording as well as the screenshots of my screen. Okay, and I would request you to note it down, and as and where you feel some amount of difficulty, just share your notes with me, and I will try to help you the best way I can to make your notes more understanding. Okay, use colors in your notebook and make notes in your own words. Don't use very textbook language. The minute you start using textbook language in your notes, it becomes very difficult for you to understand. If you wanted to write everything there is in the textbook, you could have just photocopied your textbook. Read a sentence and write what you understand by that sentence and put it in your notebook. All right, so this is where I'm going to stop with the recording.